Or here, optical coupling, when you just engineer these strong magnetic fields in very narrow systems that have sharp boundaries, you see that the cyclotron orbits get interrupted at the edge of the system, and then you get skipping orbits here. This is a nice image from the group of Jens Spielmann at JQI. But in all these experiments, independently of the method that you use to engineer your artificial gauge field, you're engineering classical gauge fields, a static background for the matter. So what do I mean by that? So basically, you just take the method of your choice to engineer a vector potential, and then from spatial variations of it, you can get a magnetic field. For temporal variations of it, you can get an electric field. And this vector potential dictates the motion of the matter. But in nature, we know that matter back acts into the gauge field itself. And this is something that we would like to emulate in our quantum simulators. And actually, what we would ideally want to do is to get this vector potential and make it a quantum dynamical entity, really promote it to an operator in order to quantum simulate gauge theories. And why is this quantum simulation of gauge theories cool? Well, on one hand, because you could then emulate in your labs some interesting effective descriptions of strongly correlated systems, condensed matter systems, for example, but also because you could try to push the boundaries of quantum simulation from simulating condensed matter models, which is what we do most of the time, to other areas of physics. For example, you could think of simulating the gauge theories that describe the interactions between elementary particles in a high energy physics context. So of course, this is a super ambitious goal, and there have been many theory proposals on how to try to merge quantum simulation and gauge theories with AMO systems. You have a nice review here that really describes many of the attempts made on that. But actually, when you're an experimentalist like me, you realize that what there are mostly in this field are theory proposals, but there are not so many experiments. And this is not because experimentalists are not interested. Of course, it would be fantastic if we could, in our cold atom labs, emulate physics of QCD, for example. I mean, maybe we would get intuition of what QCD is about, experimentalist intuition, but because this is very hard experimentally. And one big reason why this is very hard experimentally is because in this type of models, the gauge fields are dynamical. That means that they have propagating solutions even in the absence of matter. If you think of QED, even in vacuum, you have the photon, and the photon propagates even if there is no matter there. So that means that if you want to simulate something like QED in your cold atom lab, you have to overcome many challenges. The very first of them is that you need two species to simulate your model in principle, because you want to have particles that play the role of the gauge field and particles that play the role of the matter field. So then already two species model. Then the second thing is that you need to engineer coupling between both, matter gauge field coupling. For example, I mean, you want minimal coupling for QED, and then, and that's the hard thing, you need to enforce a local gauge symmetry in every point of space and time. If you want, again, on the example of QED, you need to make sure that your system fulfills Gauss law. Yeah, and that puts many constraints of the motion, concerted motion between the gauge and matter particles. Even though this is not so easy, there has been a lot of progress over the last 2-3 years on that. So building blocks, really the main ingredients required to engineer these models, have been implemented in small systems of 1, 2, 4 particles by several groups. Then in order to go to larger systems, one has gone to one-dimensional systems. And there, for example, you can use a trick, which is to use the local symmetry constraint of your theory, your Gauss law, to eliminate the gauge field in terms of the matter field. So then you get a theory for matter alone, but this comes at a price of having more complicated interactions. And this is what has been done, for example, with trapped ions or with Rydberg atoms. And over the last year, there is a beautiful work that actually manages to implement a 1D gauge theory, a so-called quantum link model, keeping both the matter and the gauge field degrees of freedom. And this, I think, Philip Hauke will probably talk about more about it on Thursday on his talk. But actually, Whereas most of these experiments, they were really trying to emulate QED, basically, like show how you can build these gauge theories and focusing on this example. What is also nice is that, of course, you are not restricted to that, but you can also at the same time emulate gauge theory models relevant in condensed matter physics, for example, in the description of spin ice or spin liquids. And actually, if we think from the condensed matter context, there are other types of gauge theories that could be also interesting to simulate with cold atoms, which are the so-called topological gauge theories. And these are very special types of gauge theories because the gauge fields do not have propagating solutions. It's not that they don't have dynamics, but it's locked to that of matter. But that does not mean that these gauge fields do not have an effect. Actually, they have a very strong effect on the matter they couple to because they effectively change the quantum statistics of the particles. That's why they're also called statistical gauge fields. And a very good example of where these gauge theories emerge are fractional quantum Hall systems because these topological gauge theories, they constitute a good effective description of them. So let me explain you that a little bit more. So you have, for example, a 2D system of electrons subjected to a very strong magnetic field. And we know that this is a cool system. The fact that the electrons describe cyclotron orbits and that their levels are quantized in Landau levels, this gives anomalous conductance to the system. That's what gives the integer Hall plateaus. But there are also fractional quantum Hall plateaus, which are not explained from the single particle level and which are really cool because in these fractional quantum Hall states, you have systems with excitations that when you exchange them are neither bosons or fermions, but they can pick up any phase, so they are anyons. And now it would be nice, I mean, this is a pure interaction effect, but it's nice to get an effective description that is single particle-like, that gives you an intuition of what's happening in the system. And this description exists for fractional quantum Hall states, and it's a topological gauge theory. So it builds on the idea of Wilczek of flux attachment. So you take non-interacting particles, the electrons, and you say, okay, all the effect of the interactions and so on, it goes into the electrons grabbing part of the external applied magnetic field to form composite objects. So this is called flux attachment because the particles grab flux tubes of this external magnetic field and just form some new particle, that's composite particle. And now what happens is that this composite particle is like a fat electron. It has its own cyclotron orbits, it has its own Landau levels, and you can understand the fractional quantum Hall plateaus as the filling of the Landau levels of these composite particles. And you can also understand intuitively well why these anionic statistics, because when you exchange these objects, then there is the Aronoff bomb phase associated to these solenoids that takes a place, and that's what gives you this phase, the statistical phase, which is not 0 or pi, so it's not bosons or fermions. And a key ingredient in this model is actually the magnetic field created by all these flux tubes. This is proportional to the density of matter because each particle has flux tube attached, and it's called the Chern-Simons field because this is exactly the local symmetry constraint of the theory that describes this system, which is a gauge theory. It's a so-called Chern-Simons gauge theory. And then what we would like is to simulate this type of physics with ultracold atoms, so simulate these topological gauge theories. So you could wonder if this is any easier than to simulate the dynamical gauge fields I talked about before. Well, actually, it's a bit simpler because you don't need two species of particles. You just need to engineer a density-dependent gauge field. But still, you have to engineer matter gauge field coupling and, very importantly, to enforce this local gauge symmetry. And there have been many efforts in this direction. So building blocks made with superconducting qubits, neutral atoms, Rydberg atoms, and even such density-dependent gauge fields engineered in an extended system in the group of Cheng-Ching in Chicago. But in all these experiments, the local symmetry constraint was not implemented. And what I want to show you today is how, by going to one dimensions, we actually can engineer 1D topological gauge theory. So with this, I come really to the outline of my talk. So I will first tell you which theory we make. This is the so-called chiral BF model. And then I will explain how we engineer it in our cold atom lab and what are the observables that we see. So let's start from the beginning, the theory that we make. So the theory that we make is the theory that you get if you take Chern-Simons theory and you just reduce it from 2 dimensions to a single one. So you shrink one of the dimensions here. Yeah, and this is a model that was proposed in the 90s by Silvio Rabello and then studied in quite some detail by Roman Jakiv and collaborators. And indeed, Jakiv took a keen interest in this model because it builds up on previous work of his on this beautiful paper here. So many people ask me, why is this called the chiral BF theory? Actually, it's called the chiral BF theory because if you write the Lagrangian of this theory, the first term reads just BF, where F is the electromagnetic field tensor, and B is actually a bosonic field, which is proportional to the vector potential in the dimension that we've removed. And then the word chiral comes from the second term of the Lagrangian, this self-dual term here, which is actually added a bit ad hoc when you do this dimensional reduction by these people in order to make this 1D system essentially reproduce the physics of the edge of the 2D system you started from to give it chirality. And then you have here extra terms that couple matter. Here I took it bosonic to vector potential. Yeah? So now if we look at the equations of motion of this system, I've written them here. We have 3 equations that we can combine into a single one and tells us that the electric field of this model is proportional to the time derivative of the density of matter. So that is linking the dynamics of matter to that of the gauge field. And these we can rewrite as the vector potential being proportional to the density of matter. And it's at the same time the equation of motion of the gauge field and the local symmetry constraint of the theory. This is equivalent to this B proportional to N condition that we had for the Chern-Simons theory. And it's really the equivalent of the Gauss law for this theory here. So now if we want to implement that with cold atoms, we don't like this Lagrangian too much, it's too complicated, but we can play some tricks to bring it to something amenable. And the first thing is to go to Hamiltonian formulation, and the second one is to use this constraint actually to eliminate the gauge field in terms of the matter field. And then when we do that, we get a pretty simple model. You can see it here. So we have a Hamiltonian that describes bosonic particles that are minimally coupled to a vector potential. And the funny thing here is that this vector potential is proportional to the density of matter. So it's an operator itself. And as I said, it's equivalent to the B proportional to N that you have in the original Chern-Simons theory. And now this looks very simple, but actually you have to think that because density is in here, we have in this vector potential that is proportional to density, and this is equivalent to an interaction term. It's equivalent to matter with some very unusual interactions, which are not of the density form that we normally have, but of current density. And if we think what this means, it's good to take a wave packet, for example, a matter wave packet, then the current operator is nothing else than the velocity of the particle, so k over m times the density. Then we see that we have to engineer matter with some chiral interactions that are proportional to density, but also proportional to momentum, so that explicitly break Galilean invariance. And now, just to finish on the introduction, why would we want to do that? Well, because if you think what makes this 2D system interesting is that they have anionic excitations, and people propose this model as a possible model for linear anions, so the equivalent of anions, basically in the simplified setting of 1D. And although there has been a long debate whether this model has linear anions or not, this was settled at the end of the 90s by Kundu, showing that actually this model is the limiting case of so-called linear anion theories in the continuum. And for cold atom people, this is actually the continuous version in a certain limit of the so-called anion Hubbard model. And actually, this controversy was pretty nice to have, because what people also realized then is that this model has very rich physics, because it also contains so-called chiral soliton solutions for the matter field. So you can have some wave packet that when you move in one direction for the matter field expands, but when you move in the other direction, it remains self-bound, it forms a soliton. So this is the model that we want to study experimentally. So how do we do that? Actually, we use a very old trick to engineer gauge fields with cold atoms. We take 2 internal states of an atom that we couple with 2 counter-propagating lasers via 2-photon transition. And by doing that, we create dress states of atoms and photons. we focus on the lowest dress state here. And we see that depending on the detuning of this coupling field, the position of the minimum of the dispersion relation moves around, and it looks like a static vector potential. Yeah? This is a single particle description, but it still holds if you go to systems where the interactions are equal, which is what was studied by all the groups that use this trick in the field. But now we just add one ingredient, which is that we make these interactions very unequal. And what this does is actually shifts the energy of these up and down atoms differently, yeah, due to the mean field interactions. And it makes that the detuning of this two-photon process becomes density dependent. It depends on the difference of the interactions between the two states. And what was shown is that then this density-dependent vector potential is proportional to density, and the group of Patrick Oberg showed almost 10 years ago that the Hamiltonian of the system is exactly the one of the BF theory at the mean field level. And now when you're an experimentalist, you might like this idea much, but then the first thing that you do is you put numbers, and then you realize that this result is derived in a limit that you can never do in your lab, at least with alkali atoms, because you need super large Rabi frequencies, so super large intensity for these beams that limit the lifetime of your gas so much that it's totally experimentally unrealistic to do it in practice. Yeah? However, we thought that physics should be continuous, so maybe we could still find a trick to do it in the lab. And for that, actually, we realized that if you look at these stress states, I mean, I put them in this color scale. This is because their internal state composition changes. Yeah? And this stress state composition is momentum dependent. This is exactly the trick that you use to shift this minimum and make vector potential. But actually, in my group, we had also studied how atoms in such superpositions of states interact. And we see that these interactions, they depend on the state composition very much, because if one state interacts more than the other, then when you are mostly in the blue state, then you interact little. In the green, you interact more, and in between, in the superposition of the two, then you interact in between. Yeah. And then if you put two ideas together, then you see that the effective interactions change with momentum. And you can see that if you put yourself somewhere in this curve, then if you remain to small momenta around this point, then interactions will be kind of proportional to momenta, because this is linear. So we can expect chiral interactions in this system, which, as I just showed you before, is the same as having a density-dependent vector potential. So this is a hand-waving explanation, but we can do a formal derivation of that and actually derive that the Hamiltonian of our system is exactly the one of the BF theory, with the bonus that we demonstrate that at the quantum level. So that's why I have operators here everywhere. And this result is valid for accessible values of omega, and also valid for different momenta, provided we take the right detuning for the coupling field. So now let me show you how we do that in the lab. So how do we probe this system? So we make this system with potassium 39 VCs, which are nice because they have tunable interactions. So we can engineer these chiral interactions. We take two states that have very different scattering lengths. One is positive and vastly tunable with a Feshbach resonance. Another one is very small, sometimes positive, sometimes negative. Also, interaction between the two states are very small. And then we make our BC, we subject it to the Raman coupling beams to engineer this vector potential. We just confine it transversally strongly with an optical dipole trap, this waveguide here, and we image it in situ with a high NA lens. And here you see the coils that we use to engineer the magnetic field. So now an important thing in this model is what happens when you give momentum to the atoms in one direction or the other, because I showed you that these interactions, they need to be chiral. That means linearly dependent on momentum. So we also add to this system two additional beams, which we use to induce Bragg transitions and then kick the atoms to the left or to the right. So give different momenta to the atoms. So now what do we get when we do that? So, well, we create the system subjected to the Raman coupling, we kick it in one direction, and then we immediately let it expand in this waveguide, so free in this waveguide. And this is what we see when we kick it to the right. We see that the cloud starts to expand, whereas when we kick it to the left, we see that the cloud remains without dispersion for all the times that we observe. So what you are seeing here directly is that the interactions of the system are different when it's moving in one direction or the other one. Actually, when it moves to the right, we are creating a system with repulsive interactions, whereas when it moves to the left, the system is attractive, and that's why the behavior is so different. And we can actually see that the size of the system after clicking it, then it's very, very different in the two cases. So we are showing that this system is chiral in the sense that it depends, its properties depend on propagation direction. Its interaction properties depend on interaction direction. And when we move to the left, actually, the fact that the system does not disperse at all during propagation is showing us that we are forming a self-bound state, a bright soliton. Now, I told you that people were interested in this chiral BF theory because it had chiral soliton solutions. So can we say something about this soliton that we create? Is it a chiral soliton? So for that, what we do is that we implement experimentally what you would think about of doing theoretically. It's that we build a wall for the atoms. That's a focused repulsive laser beam, and then we see what happens. And what happens is that this soliton comes to the barrier, and then when it bounces off, it starts to expand. And you could wonder if our barrier is doing something bad for the atoms, but standard solitons actually that we can also create don't show this behavior. So actually what we are showing is that we have really a chiral soliton in our system, really the chiral soliton solution of this BF theory. Now, the last point. So I told you this chiral BF theory, it comes from having a vector potential, this BF gauge potential that is proportional to the density of matter. So how can we see that experimentally? So actually, to see that, we have to think that we have to see a vector potential. And of course, a vector potential we cannot see directly. We need to see a difference of it or a time variation of it. So what we do is to look at the time variation of the BF vector potential, which is the same as looking at the density variation of matter. So we will change the density of matter, and then we will see if we see something appearing in our system. We want to see an electric field appearing to see the back action of the model. Now, that's what we do here. We change this BF gauge potential by changing the density of the system, expanding the cloud. So we prepare the system here subjected to these Raman beams. And then at t equals 0, we just let the atoms expand in the waveguide. And what we see is that the system shows funny dynamics. Actually, it starts to expand, but at the same time, it develops a tail on one side. So the cloud profile becomes very, very asymmetric. Now, why does this happen? Actually, microscopically, you understand it very well. It's because the state composition of the system depends on momentum, and the two states interact differently. So when we let the atoms expand, then the atoms that fly to one direction are in one state that interacts differently from the atoms that fly in the other direction. So the atoms that have more interactions, actually, they have more interaction energy to release. So they just expand further, and that's what gives this asymmetric profile to the cloud that we see here. But we can also interpret that in terms of a BF electric field, because basically we have the density that drops over time different in different parts of the cloud. We need to fulfill the continuity equation. So obviously the density drops in the center and increases in the edges, but it increases differently in the two edges of the cloud. It pulls more in one direction than the other, and that's what gives the asymmetric form of the cloud. And now this is something that I explained you hand-wavingly, but we can compute theoretically. This is what I've put here. So the dashed lines are numerical simulations of what we expect for our system for realistic experimental parameters, just considering the full system, the BEC with the Raman beams and all that. And the solid line is just the BF theory. And you see that the two agree very well. So our BF theory captures very well the behavior of the cloud. And also from the BF theory, we know what's this electric field. These are these arrows here. And you see exactly the distribution of forces that I was telling you before. These forces are the ones that are distorting the cloud profile. So that means that if we want to know about this electric field, then we need to characterize the asymmetry of our cloud upon expansion. So we do that by introducing this so-called skewness parameter. That's a number that is positive when the cloud has a tail to one direction, and negative it has the tail to the other direction, 0 for a symmetric cloud. And it's nothing else than the third moment of the distribution divided by the second moment of the distribution cube. And then this is what we see experimentally. This skewness measured experimentally and simulated theoretically, they agree very well. So you could think, okay, that's it. That's the density-dependent electric field. Actually, things are a bit more complicated because there are two different contributions to the cloud asymmetry, one from this electric field, but also one from kinetic effects, basically a momentum-dependent effective mass. So if you don't choose the detuning of your Raman field right, you can also completely cancel these two effects. But there is a sweet spot in between where actually these kinetic effects, they cancel out. And we only have the electric field effects. And actually, this is one of the conditions that we have to map our system into the chiral BF theory. So the fact that we see asymmetric expansion here is actually directly a manifestation of the back action between matter. We change the density of matter, and then we have an electric field that appears. And with this, I really come to the conclusion of my talk. So I showed you an example of how we can engineer a gauge theory with Bose-Einstein condensates. In our case, we realized for the first time a 1D topological gauge theory. This theory that we engineer is the so-called chiral BF theory that was proposed in the 90s. It's the same as having a density-dependent vector potential minimally coupled to matter. This is equivalent to engineering a system that has chiral interactions. And these chiral interactions, experimentally, we realized by combining Bose-Einstein condensate with tunable interactions and Raman coupling. And we observed the two main manifestations of this theory. On one hand, the chiral soliton solutions that exist for the matter field, and on the other hand, the fact that there is back action between matter and gauge field. And now this opens the door to many new experiments that we are now starting to plan. One thing is that we can go to one-dimensional systems. Here, for the moment, we still have some transverse excitations left over in our system because we don't confine it strongly enough. If we go there, then our system should allow us to engineer these linear anion models and see statistical transmutation. And then the second is that there is a nice route already proposed to extend this scheme to two-dimensional systems and really engineer a Chern-Simons gauge theory by using, instead of counter-propagating Raman beams with angular momentum. And with this, I want to show you the people that did the work since this paper is not yet published. So these two PhD students, Annika and Craig, and two postdocs, Eletra and Ramon, with contributions from former members of my group. Cesar is now in Munich, and Julio is now in industry. And we have to acknowledge theory support from Alessio Celli from UAB and Innsbruck, and also many theory discussions with our theory friends in Barcelona and elsewhere. And with this, I want to thank you for your attention.
All right, thank you very much, Leticia, for this exciting talk, interesting new results. Are there questions? I'm looking to the Slack channel. Please type your questions for Leticia into the Slack channel. Maybe I start already and we see as the questions come in. So so far, maybe you can say something a bit about the range of tunability in the interactions. So in your case, I saw you had this 20 A0 and minus, was it -5 or the vice versa? So how much tunability do you have on the interaction strength, on the effective scattering lengths that you see in those?
So this, of course, is limited by the range of the interactions of the original system. Actually, it could be much more broadly tunable than what I showed here. We wanted to restrict ourselves to a not too big range, because if we put too large scattering length in one of the initial states, then we go out of the mean field description. And then, I mean, of course, for a demonstration experiment, we want to make sure that everything is described by mean field and we can do the numeric simulation and compare to the experiment and so on. But of course, we could go further from that and it would still hold. No?
Mm-hmm. And
so this was more us limiting ourselves to weakly interacting and everything more than a real limitation of our setup.
And in the guide that you have, how much 1D is the system actually, and how much do you rely it to be 1D, and or how much do 3D effects change?
So we are not 1D at all. We, I mean, we have 3D GPE, all these simulations. It's just the dynamics is this BF theory in this direction, and the transverse excitations. I mean, actually, we can see in some data, we can see some small breathing but we can derive a model that has the transverse degrees of freedom, and that works well. Of course, if we want to see anions and so on, this does not work at all, because then you would want to see the exchange, and now the particles can turn around, right? So we wouldn't really need to confine to one dimension if we want to see this type of physics. Yeah? So for the observables that we looked at, for the moment, it does not matter, but for other things, of course, it matters.
Okay, so we have now a question. Very nice talk. Can you elaborate? How do you tune the Raman lasers to make them density dependent?
Okay, so maybe I was a bit too fast on that. So what we do, we don't tune anything on the Raman lasers. What we do is to make interactions different between the two states, and that makes all the job. Yeah? Because we tune interactions such that actually the energy of these up atoms is not the solid line, but the dashed line. Yeah. And this energy depends on density, and this one of the down atoms the same. Yeah? It depends on density. And now we set constant, basically the detuning here to 0 of the Raman lasers, but because there are these density inhomogeneities on our cloud, yeah, then interactions are also different. So these lines change with density, and that gives a detuning, and this gives a density-dependent vector potential. Yeah? So the system does it on its own as soon as we set the interactions right.
Okay, can I ask final question? So in the extension to 2D, can you comment a bit on that? Say a bit more how this would work in 2D?
Mm-hmm. So then the extension to 2D, this is a proposal from the group of Patrick Oberg also. In theory, it's very easy. You just change counter-propagating Raman beams by Lager-Gauss beams with angular momentum, and everything should work the same, except that then it's a 2D system, so you have basically a vortex basically on the coupling field. In practice, this derivation is done for very large omega, so it's done in this adiabatic limit, which I explain. It's not something you can access experimentally, at least with alkali atoms. And you need an atom that at the same time allows you to set very different scattering lengths. Ideally, that has only contact interactions, because if you have a dipolar atom, you also have dipole-dipole interaction. So it's complicated on top. But at the same time, you cannot put omega so large, because we have a lot of heating from photon scattering. Yeah? So then if you put all these constraints together, omega very large does not work. So we would need to rederive their results microscopically from this interaction model that we did, and see to which extent their proposal still holds for our system. We are optimistic it holds to some extent, but of course we still need to do quite some theory and then the experiment.
Okay, great. We're just on time. Perfect. So thanks a lot, Leticia.